Morning. I am Amílcar Soares, and I'm going to present a new method of geostatistical seismic inversion, but with the self-learning stochastic simulation algorithms. Okay, let me recap briefly the main outline of geostatistical seismic inversion. Well, it's a method to integrate seismic data in our models of elastic properties or acoustic properties, but is a typical try to solve a typical inverse problem. We know the solution, which is real seismic, and we want to create models of our elastic properties that match the real seismic. Okay, as it is a hill post problem, normally it is solved with kind of iterative procedure, optimized iterative procedure. Basically, this one, geostatistical inversion, consists in three main steps. In the first step, with the stochastic simulation, we generate an ensemble of models of our properties, elastic or acoustic. Through a forward model, we transform it in synthetic seismic responses, okay? And we compare synthetic seismic with the real seismic. Here, in this step, we must have a kind of optimization algorithm, kind of genetic algorithm, for example, just to assure that this iterative procedure converges to the solution I wish. Okay, so in the next iteration, we perturb the previous models with the co-simulation until I reach a good match with my real seismic. This is basic. Now let me show you the self-learning. What do we mean by self-learning simulation algorithms? And I'm going to show you a very simple and naive example. Suppose we simulate, we get an ensemble of realizations through a stochastic simulation, okay, based on a variogram model, a global probability distribution function, and so on. So this ensemble of realizations of my property, for example, acoustic or elastic property, I can create for each cell, I can compute the local variance or the local distribution. And we can see, for example, areas with low uncertainty here. For example, that comes from a local distribution, a very narrow local distribution. And there is also with high uncertainty that comes from more spread, high uncertainty, more spread and high uncertainty distribution. So the idea is exactly to use again those simulations like in the seismic inversion procedure, but now with the new local model instead the global one. Okay. In summary, what can be updated from the simulated ensemble? For example, local statistics driven by the experimental data, well data, geophysical data, or production data. And we can update local uncertainty and local variogram, local patterns like variograms or spatial covariance. So in short, by adding more data, we succeed to update global a priori models, obtain local models. So we have the data, we have to create the global models, we do the simulation or co-simulation, and we update model statistics, local histograms, variograms, and so on. Now, the challenge, this is the challenge. How can we capitalize in next simulated ensemble what we have learned before by adding more data? Okay, and the solution is simple. It's just to integrate updated model in this loop here, in the third step here in the optimization. I'm going to show you two illustrative examples for to make more clear this concept of self-learning. First example is updating local models of covariance and isotropy in geostatistical seismic inversion, just to reach those stationary patterns of channel structure. We start by a global covariance model, and we try to update and to get those local diagram models or covariance models, okay, anisotropy covariance models. The second example that I'm going to show you is to update using the updating of local distribution in geostatistical seismic inversion. It means that after I simulate the ensemble of realization, I compute in each cell the local distribution that are going to be used in the next iteration in the co-simulations and so on. Okay, starting by the first example, how the updating of local models of covariance and anisotropy, how these local models, how can I calculate those? I calculate those local models. For example, after we simulate, we get the mean IP models, okay, and in each point, in each location, spatial location, I will try several templates of different anisotropy model, and I will choose the one that will with the best fit of this local feature. Okay, in this case, it's represented in 2D anisotropy ellipse, but at the end, as you run in 3D, I will obtain a map. In each point, in each cell, we have the best local ellipsoid. Not only the direction, but also the ratio of anisotropy of this ellipsoid. So in short, the outline of the geostatistical seismic inversion is like this. So I simulate the N models of acoustic impedance with forward model. I obtain synthetic seismic and I do the optimization. The optimization by comparing with the reference seismic. I will obtain the best parts of each model, which is best IP model, the best measures of similarity of those models. This is the classical part, okay? And also the map of the local covariance models, the isotropy covariance models, okay? Let me show you one result. This is a synthetic case, so I know the reality. So this is my real image that I want to obtain of acoustic impedance, okay? And in the top, I put here an exercise made only by GSI, just a seismic inversion, but with just one model, global covariance model. And here, with the proposed algorithm, which is local updated diagram models, as you can see, even the seismic, because this is a synthetic, even the seismic is extremely good. With just one global, it produces good results. But it will, even so, with this new method, succeed to improve even better the final results. Let me show you a real case study. This is just a cross section. Okay, this is the real seismic, the seismogram, the last iteration obtained with the proposed model, updated model, and with the classical GSI. But where we notice the advantage of this new method here, this is the final IP acoustic impedance obtained with the proposed model, the local updated, and you can see that the features, with those features, those channels, those layers, the shape of those layers are quite very well reproduced here. And while here in the classical GSI, in this situation, you can notice here some artifacts produced by the global diagram model, just one model. Okay, so it's a clear advantage of the proposed method. Now, the second illustrative case, which is GSI with self-updating local distributions. The outline is pretty the same. as the previous one, I generate a set of models, I create a synthetic, I compare with the seismic, but here in each cell, I compute the local distributions. Okay, those local distributions are going to be used in the next iteration for the co-simulation to perturb those models of IP. Okay, let me show you one case study. It's a real case study. Here we have several wells. This one was taken out just for a blind well test, for a blind well. So we have used only 4 wells, okay? So, and this is the correlation coefficient that we obtain for all, along all the simulations. We reach 0.79, which is quite good match between the seismic and the seismogram. But let me show you this is the seismic and the seismograms, the final one in the polyline, the cross-section following the polyline of those wells, okay? But I want to show you this picture is with GSI and the proposed method with local probability distribution functions, where you can see the layers, all the layers, the distinction, all the contrast between the layers of extreme values of IP are pretty much well reproduced with the new method. Okay, but let me show you the exercise of blind test. That one that was taken out, that was not used to produce the model. So this is the GSI with local PDF, and this is the classical GSI. One thing that it is important to notice is a clear advantage. The new method enlarges the space of uncertainty. Here in green, it is plotted the P10, okay, and the P90. The percentile, 19th percentile. And you can see it enlarges uncertainty, which is a clear advantage, which makes that the real values of the blind test well, the most of those values drop in that interval in case of the new method, something that would not happen in the classical GSI, exactly because the space of uncertainty is pretty much more narrow. Okay. Now let us go to some final remarks. Local statistics are updated based on a misfit between simulated and observed data. So the proposed method is a data-driven learning process. In fact, second, the use of local PDFs ensures variability within the ensembles from different iterations and the convergence of the inversion procedure. So, and also it reproduces the non-stationary spatial patterns of maniform channels, okay, as you could see with this updated of covariance and isotropy models. Finally, I would like to emphasize that this methodology can be extended to other types of data, production data, and other updated statistics, multivariate distributions, for example, between VP, VS, density, porosity, etc., in elastic inversion or direct porosity inversion. Okay, before to thank your attention, I would like to show here the 2 publications that about the methods, those 2 methods that I've shown to you. Okay, this is some acknowledgements, and thank you for your attention.